Betelgeuse is a massive star, perhaps 15 or 20 times the mass of our Sun, and it is near the end of its life. It is an enormous, luminous star that will one day go boom. Recently, renowned physicist Brian Cox has given the world something to think about. According to him, one of the brightest stars in the constellation and night sky, Betelgeuse, the red giant star, is on the verge of a supernova explosion. All data received by astronomers also confirm this impending catastrophe. Now, we wonder, are we about to witness a disastrous supernova explosion, or is it mere speculation? Let's find out the dangers surrounding Betelgeuse and look at the warnings Brian Cox has given about this supernova. The giant red star of significant proportion, which earned its name as Betelgeuse, shines brighter than most of its counterparts and is located in the Orion constellation, particularly the left shoulder. Although it has long been in the focus of observers due to its distinctive features, the recent findings about it have intensified curiosity and interest in the giant celestial body. Naturally, a star is considered a regular supernova if it measures about 8 times the Sun's weight. However, the celestial marvel Betelgeuse breaks all protocol by being more than 700 times the size of the Sun. Much more than anyone can imagine and about 15,000 times more massive. The recognition of this giant star can be traced back to the Greek astronomer Claudius Ptolemy, who was secretive about the star's attributes when they were not readily known to all and were limited to color and position. Following advancements in instruments and investigations since then, it has become easier to analyze celestial bodies like Betelgeuse and gain insight into their properties. The giant red star Betelgeuse seems to be aging well, increasing in mass as it continues to exist. The star is about 8 to 8.5 million years old, a senior age in stellar measurement but relatively young in human terms. With its physical properties, it is safe to say that if its vastness were visualized compared to the solar system, it would most likely displace the first 4 planets, including Earth. How this giant red star managed to gather this mass leaves scientists in awe and has merely increased interest in the star. Scientists have helped us understand that its size is not a mere happening but a stage in its general stellar life cycle. In this life cycle, the stellar giant is presently in its twilight phase, marked by expansion, cooling, and the fusing of hydrogen into helium in its core. Its current phase, being giant, red, and hot, is known as the supergiant phase, which represents the culmination of millions of years of evolution involving various processes and changes. These transformations have managed to alter it from the hot blue star it once was to the giant red star it is now, a change influenced by nuclear fusion and gravity. The color change of Betelgeuse is due to the cooler temperature of its surface compared to other stars, including the Sun. The Sun's temperature is about 5,500 K, whereas Betelgeuse's temperature is about 3,500 K, allowing it to cast light at wavelengths that make it appear red. Just as its size is a result of its growth phase, its color gives information about its condition, gaseous exchange, and vastness at a given time. Ancient texts of the Chinese and Romans have deduced that about 2,000 years ago, the giant red star was mutually yellow, and the first record of it being red was in the 9th century, as described by Arabic scholars, giving clues to its evolutionary path. Aside from its color, its brightness is another physical attribute to consider. Betelgeuse is a semi-variable star, meaning the intensity of its light increases and decreases over time. This property of luminosity has fascinated astronomers and astrophysicists over the years. Betelgeuse usually follows a 400-day cycle, with a longer cycle spanning about 5 years, documented since 1836 by Sir John Herschel and possibly earlier by Aboriginal oral traditions. Despite these features, the wonder of Betelgeuse is not solely based on its color change or brightness but also on the irregularity with which it exhibits these changes. Unlike most stars that follow a particular pattern, Betelgeuse changes its intensity, dimming and brightening irregularly. This unique feature reveals more about its form and internal processes. Recently, the giant red star captivated astronomers and stargazers worldwide with an unexpected change in appearance and color, known as the Great Dimming. In 2019, Betelgeuse began dimming mysteriously, losing brightness at an average of 0.1 magnitude per day, and by February 2020, it had reached its lowest luminosity. The star dimmed roughly every 430 days, with dark spots or star spots appearing on its surface during each cycle. Despite being visible to the naked eye even in light-polluted areas, the star seemed noticeably fainter during this period, leaving observers in awe. The phenomenon surrounding Betelgeuse poses a paradox because the light we see is not in real time but as it was in the past, about 725 years ago, due to the time it takes for light to travel to Earth. This creates limitations in predicting the star's changes and future events. Investigations using the Hubble Space Telescope analyzed Betelgeuse's patterns and properties, providing unique insights into its dynamics as a variable star. The Hubble's sensitivity to ultraviolet light allowed researchers to examine different surface layers of the star, revealing processes involving turbulent convection cells. Additionally, the ALMA Observatory in Chile delivered ultra-high-resolution images, highlighting features like the expansive gas plume extending from the star's surface. In February 2021, Betelgeuse underwent another dim cycle, registering a V-band magnitude of plus 1.64, dimmer than its usual brightness. Star spots, where the magnetic field is most potent, create cooler areas on the surface and influence its brightness. Betelgeuse's magnetic field is believed to be thousands of times stronger than the Sun's, trapping gases in loops and creating zones of intense magnetic activity. These star spots, larger than Earth and covering up to 20% of its surface, play a massive role in the star's brightness. As Betelgeuse nears the end of its life, scientists speculate on its future, with theories suggesting mass ejection and dust formation as precursors to a supernova explosion. Investigations with the James Webb Telescope revealed that years ago, Betelgeuse underwent an eruption, losing a significant portion of its visible surface and emitting large amounts of dust clouds, providing further clues to its impending fate. Occurrence while dimming is natural for dying stars. The other events are uncommon and baffle scientists into probing for answers. The Sun, although seemingly unchanging, continues to undergo several outer atmospheric losses in coronal mass ejections. Nothing has come close to that of Betelgeuse. Using the James Webb Telescope, scientists can discover more reasons for the mass ejection. According to findings, the stars lose their mass as the nuclear fusion begins to extinguish. In different supernovas, the mass loss rate will therefore influence the fate of the star, and regarding the mass loss of Betelgeuse, it could be inferred as a likely prelude. The conclusion from the Hubble Space Telescope is that the dimming of the giant star was caused by an ejection of a hot material into space. The material ejected then formed a dust cloud, which covered the surface of the star and reduced the amount of light reaching Earth. The dust cloud was formed from plasma of very high temperature, which erupted from a convection cell on the star's surface, moving through until it settled on the outer layer. As the temperature dropped and the erupted material cooled, it settled as dust particles that blocked light on the star's surface. The ultraviolet light spectroscopic observations of the Hubble Space Telescope were essential to ascertain the exact period of the final darkening of Betelgeuse. The ejected mass was then calculated and seen to weigh about 400 billion times the mass typically released in a standard mass ejection, weighing more than Earth's moon. The giant star moves around at about 67,000 miles per hour relative to its surrounding interstellar medium, creating a bow shock. The bow shock is the wave formed by the wake of a moving ship as the star travels. This phenomenon is better seen as the star's outer layers interact with the interstellar gases and dust, providing a spectacular testament to the dynamic nature of the star and its interaction with the cosmic environment. The phenomenon is important as it helps to inform us about the current state of Betelgeuse and contributes to our understanding of stellar evolution and the process of mass loss. It has also been observed that since the ejection of the large mass, the star has been in an unstable state. From hydrodynamic simulations, suggestions have emerged regarding a connection between the star's convective activities, mass ejection, and subsequent pulsation mode switching. The driven pulsation responsible for mass loss is limited due to the constant energy dissipation through shock heating. A professor at the Massachusetts Institute of Technology, Salvatore Vitali, reported that the detected wave from the direction of Betelgeuse may not have originated from it.